Today, we will discuss potential energy diagrams. So let's start with the on left side you have reactants and on the right side you have products. And the highest point of this graph is transition state, which is also called activated complex. On y-axis you have potential energy and on the x you get reaction coordinate. If you see the diagrams, you see products have less energy than reactants. This reaction is exothermic. It means energy is released out of the system into the surroundings. So, the enthalpy of reaction is negative. What is enthalpy? It is the difference between the potential energy of products and reactants. So, if we minus product energy with reactants, we get the enthalpy. As we already know, the energy of product is less than the energy of reactants. So you are going to get the negative values. But question arises here. So what's the difference between transition state and reactants? This is forward potential energy. We need this activation energy to start the reaction. Without this, the reaction won't start. But there is a way to reach activation energy fast by increasing the temperature of the reaction, which ultimately speed up the process. What we call the energy difference between the transition state and the products. This is the activation energy for the reverse reaction. If you want to move backward, you have to go through this way. Once you reach the transition state, that where the reaction takes place, you need enough energy to this transition state. This is talking about reverse reaction. What happened if we add catalyst to it? We knew catalyst speed up the reaction. Let's see how the diagrams looks like by adding catalyst. The activation energy is much lower as compared to previous one which have significantly high. So it means by adding catalyst, its forward and reverse activation energy is reduced significantly, as we can see on the diagram of the submarine. Now, we want to draw the potential energy diagram for endothermic reaction. How we gonna draw it? You need to draw the products above the reactants. And now it's endothermic. As we can see, delta H is positive for endothermic. So it means if we minus the energy of products with reactants, the products have more energy than reactants. And this is endothermic reaction. In this, the system absorbs energy from its surrounding. So the ultimately the enthalpy of the reaction is positive. Let's understand it by some supposed values so you that better understand it. Let's say product values are at 500, the reactants are at 800, and the transition state is at 1000. If you want to get the values of forward activation energy, it is the difference between transition state and reactants. So 1000 minus 800, we get 200, which is positive. Well, same apply for calculating reverse activation rates, which is the difference between transition state and products. So 1000 minus 500, we get 500, which is also positive. Now, let's find out the enthalpy of reaction. So it's 500 minus 800, we get negative 300. The negative sign shows that the reaction is exothermic. We can also calculate the we can also calculate the enthalpy of the reaction by forward energy activation minus reverse activation energy. So 200 minus 500 with that negative 300, which is the same as we calculate previous. You just have to remember these four equations as these are really helpful in your exams. This is just a one step reaction. Now we will see how this potential energy diagram works for two-step reaction. Remember, when we're talking about two-step reaction, in this case you have two transition states, TS1 and TS2. You can see reactants, products, but in two-step, there is intermediate lies in the middle. But here's one question. Is this the reaction exothermic or endothermic overall? Well, see, the products have less energy than reactants. So the enthalpy of the overall reaction is negative. So it's exothermic reaction. But what about the first step? What about the enthalpy at first step? Is it endo or exo? For this, we see reactants and intermediates. You can see clearly intermediates have more than the energy than reactants. So we are going up, which means system has absorbing heat. So their enthalpy is negative and it is a endothermic reaction. As we move from intermediate to product, graph going down, which shows enthalpy is negative. So it's a exothermic reaction. First step is endothermic, second is exothermic. The overall reaction is exothermic. One more thing we have to find out which step is slow or rate determining step. If you notice, first step has a higher activation energy than the second step. This makes the first step slow. Why? Because it's harder to go up that large energy state. The transition state which has highest energy linked with the slow step. Now, there is a little word for you. How potential energy diagrams works for three steps. Take a moment and try yourself. Either the reaction is exothermic or endothermic. Let me give you some hints. There are three transition states, TS1, TS2, and TS3, and there are two intermediates, intermediate 1, intermediate 2. Take the time and try to solve it. Okay, let's start with the first step. As we move from reactants to intermediate 1, it's endothermic, as intermediate 1 is higher in energy than the reactants. The second step is a rate determining step, and it is exothermic. The transition state 2 must the transition state 2 is very high. As we can see, intermediate 2 is much lower than the intermediate 1 in terms of energy. The third step is endothermic, as we go up again to reach the final products, which must be above the reactants to make the whole reaction endothermic. This is how we determine either the reaction is exothermic or endothermic by making their potential energy diagrams. But remember, highest transition states always linked with the slow rate determining step. This is also very beneficial when we study the order of reaction. If you have questions, let me know in comments. Like and subscribe for more. See you in the next one.